and the fineness or the grain size of your sand sample is very important parameter because it influences the strength of your mold and also control the permeability of your mold. And this grain size and its distribution are determined with the help of fineness testing of the molding sand. So you have a very simple apparatus which consists of number of standard sieves mounted one above the other on a power driven shaker. So these are your mechanical sieves, and just like the sieves which you use in your home to basically filter the floor used for making chapatis, and these are of different mesh size. You can see this is a coarse mesh size while other sieves are of fine mesh size. So basically you stack all these sieves over each other, and then you fix this whole combination in this particular holding device, and which is fitted with your mechanical shaker. So if you switch on the button, it will start shaking these sieves, and whatever be the sand you fill it at the top of the first sieve, it will be separated out according to the particle size. So shaker vibrates the sieves, and the sand particles on the top sieves get screened and collected on different sieves depending upon the various size of grains present in the molding sand. So the top sieve is the coarsest one. So this you can see in the combination. So this sieve is having a coarse mass, means the bigger particles can easily pass from this sieve. And this bottom sieve is the finest of all the sieves. And at the last, maybe this one or below this particular sieve, there is a final pan or the dust collector. So in that pan, it is used to collect very small particles which may not be used for the purpose of making your sand mold. And in between, sieves are placed in the order of fineness from the top to bottom. So in this way you can separate out the sand particles, and each sieve is having its own sieve number, or you can see the mesh size. And you all know that mesh size is correlated with the size of the particles in microns. And easily you can have an idea that which type of what type of distribution is in your prepared sand sample. So first of all, you take 100-gram sample of dry sand, and then you remove the clay contents with the help of the process or procedure described in the previous slide. And that 100-gram of sample of dry sand is placed in the upper sieve. So this upper sieve is mainly of the coarse mesh size, and this sample is vibrated for a definite time period. And as per the standard, this is approximately 15 minutes. And after 15 minutes, you can disassemble the sieve combination, and you measure the amount of the retained sand particle or sand samples on each sieve. And then you can easily make the distribution graph, that on the x-axis, this particular x-axis shows the size of the sand particles in microns, say 53, 75, 106, 150, 212, and maximum up to 850 microns. And on the y-axis, it shows you the percentage of the retained sand sample in what is the percentage of the sand in the sieves. And accordingly, by measuring the particle size or this measurement of sand sample, you can make this frequency curve, and also you can draw the cumulative diagram And now our main aim is to find the AFS grain fineness number. So AFS denotes to the American Foundry Society, and grain fineness number can easily be calculated, that you have approximately 11 number of sieves ranging from mesh number 12 to 270. And you all know that what's the size related with this 12 number, and what is the size related with the 270 number. And then so you have also measured the weight percentage of sand retained on each sieve, so that it is suppose, let's take an example, that you have taken a sand sample of 100 gram, and then you have performed the shaking or sieving. So this much is the percentage of sand of retain on each weight. And you can see this. This comes out to be somewhat to 99.52. And I think less than 1% it may be wasted, or it may be, I can say, it has stick to the walls of the sieves, or maybe while handling and while vigorous shaking, the sand particles can easily be can also be, can say, uh, these are not present in the total composition. And then you multiply this percentage with the previous sieve number. So before this sieve number, 12 number, before the previous number is 6, and then for 20 it is 12, means 12 is the previous number to 20, and so on. So you multiply this percentage of retained sand on sieve, and you multiply it with the previous sieve number, and you will find out the product. So finally you will have a product, and then you add this whole product of all the 11 sieves, and then you divide it by 100. So you get the average American foundry system grain fineness number. So this will give you an idea about what is the average particle size of my sand sample. So this is a very easy process. Just you require mechanical sieve and a shaker. So after this, uh, another important property we have already discussed, that the permeability. And this permeability of the molding sand is determined by flow of calculated quantity of air through a standard molding sand sample at a constant pressure. So permeability, we have already studied that what's the effect of permeability. So if there is more permeability, then the during the casting process, all of the dissolved air or other gases can easily escape out. And however, if the permeability is very high, so it may also lead to the weak mold for the casting process. And so here in this case, this permeability reading is taken by noting the time in which approximately 200 centimeter cube of air is passed through the specimen at constant pressure. So that constant pressure is somewhat 10 grams per centimeter square. And I told you that you have to calculate the flow of this air through a standard molding sand sample. So that standard sample size is approximately of 20.26 centimeter square cross sectional area, and its height is about 5.08 centimeter. So the permeability number. So you calculate this permeability number mathematically by the formula given below, which is equal to P equals to V into H upon PAT. And V is the volume of air passing through the specimen in centimeter cube, and this volume is approximately this 200 centimeter cube, and height of the specimen, you know, it is 5.08 centimeter. And pressure, this is also is constant, is 10 gram per centimeter square. And area, we have already considered that it is a standard value 20.26. And so basically, if you keep all these numerical value here, so approximately you will get this number 3007.2. And then with the help of the stopwatch, if you are able to note this time period, so you can easily calculate this permeability number. So for this purpose, there is a special equipment which is called the permeability tester, and in this particular equipment there is a tank which is filled with water, and this tank is also having one tube. So this is tube is for the passage of air, and then there is an arrangement which is having your standard sample, and to the bottom of this sample, this tube which is coming from your water tank, and it is basically connected with this sample chamber, and there is another tube which gives a reading about the pressure through a manometer. There is a balance tank which is made up of stainless steel, and the whole tank is also made up of the stainless steel material. So this balance tank is having some marking from 0 to maximum level, and within this volume, this much of the air is present, this approximately 2000 centimeter cube, and it is also having some weight. So when you keep this balance tank at this position, so it will try to get submerged due to its own weight, and whatever be the air present here, it will try to so it will so with the pressure, the air will go inside this air passage, and it will try to escape out from this sand sample. So this chamber is open from this side, so easily the air can easily pass through it. So you measure the travel of this floating tank, and you measure the travel of this floating tank, and you measure the time period when it wholly submerged into the water. So this it's basically movement, or the passage of the air is also controlled with the help of a stop valve or a variable nozzle, and with the movement of this balance tank into this water, and if you are able to calculate this time in seconds, then it will give you an idea about the permeability number. So this is the equipment in reality, where you have this chamber, and this is also filled with water, and there is a floating tank, and this is a manometer which is connected to this. This is particular the arrangement, or the holding chamber for holding your sample. So you place your sample here, and so there is so this air tube somewhat is fitted at the bottom. It is connected to this holding arrangement, and it is also connected with the manometer. So with the movement of this balance tank, you can easily measure the this permeability number, if you can calculate the time period in second with the help of a stopwatch. So this is the process or the test to measure the permeability number of your molding sand. So if you like the video, then please subscribe to my channel, share it with your friends, and don't forget to hit the bell icon for the latest updates. Thanks for watching my videos.